So today I'm going to finish up the rest of chapter 3, and then we'll start with chapter 4, which is on threads. So last time I was around here, really introducing a few interprocess communication methods. So one of them, as you know, is TCP/IP, and here's just some sample code for you to try. So TCP/IP is one where the client, you have the concept of client and server concept. A client can make requests to a server. So what it does is it names the server, and it could be localhost, or you could resolve it by name, and then say which port do I want to connect, right? On the other hand, the server would then say I want to bind to this host, and then also what port do I want to listen to, and up to how many connections. And so it's one client can connect to a server at a port, but then a server can accept connections from multiple clients. Okay, and so how do you know as a server which client are you talking to? That's why their code is somewhat asymmetric, because on the client side, you do the socket based on, just construct a socket and then do a connect to the host and port tuple. And once it's connected, then you can do the send or receive. Really doesn't matter. And on the server side, though, you do the listen, but then for every instance that client connects, you actually get a separate instance of a client socket that you send or receive with. So here, it's up to 5 at a time. So that way, as soon as you do accept, that API gives you a separate data object, kind of like a file handle with which you can do a read and write. So if a separate client connects to you at the same port, the accept will give you a separate data structure, so that you know, okay, that's here I only have C. I could do C1, C2, C3, or use a list of these objects, and then I can clearly do the connection, do the conversation with each separate client, even though they all come in through that same socket. So the S here is really the external interface, but from there, you derive the individual instances to connect with the client. Okay, so you try this code out, and then you can actually try the same server with different clients. You can open different windows, try to connect to run different copies of client code and see how that works. And remote procedure call, well, strictly speaking, it's not what you might call an interprocess communication mechanism. It's really more of the idea of client-server, but packaged up in the form of a procedure call. What's a procedure call? Well, really, if you're familiar with C, then every procedure is a function. But there used to be some distinction between what a procedure and what a function is, especially if you go back to Pascal. In Pascal, you can have something named procedure, something named function. And the only difference is a procedure does not have a return value, but a function has a return value. But these terms are used in such a messed up way that everything here is called a procedure call. But in C, everything is called a function call. They're really the same idea. In Python, yes, a void function, so to speak. There's no void type, but it's none, right? So, but yes, Python thinks or treats everything like a function, even if it's void. Right. So, but even though you can't take a void as any value for anything else. But anyway, that's just really the syntax difference, and there's really not any semantic difference. In any case, so think of it as a function call, right? And it could actually return some value. But here, let's just stick to the terminology of procedure call. So the idea here is I want to make a function call, but it's not on my machine. It's on some other server. right? And so how do you do that? And why would you want to do that? Well, because this was invented during the day where you have these legacy applications. These could be banking, could be scientific application, could be something where somebody just wrote the code and it works for a long time and nobody wanted to fix it. But at the same time, those machines become obsolete, and or you for whatever reason you just want all the procedure calls to happen on a certain machine. So what do? Well, you turn those into servers, and so instead of a local function call, and in fact some could be written in really ancient language like COBOL. You may have heard of COBOL. So nobody uses COBOL anymore, but there's still machines that run COBOL code from 50 years ago. And so what do? Turn them into COBOL RPC servers. That way you write your code, and if you need this function, make a remote procedure call. And so you don't want to say, okay, like the socket on the previous slide, I don't want to write socket code like here, from host, port, connect, send, receive. I don't want to do any of that. I just want one simple calling interface, just like any other function call, except the details of connection, return value, all taken care of, right? So that's what a remote procedure call is. And nowadays you have a web, you have XML, so XML RPC is actually pretty common. That's well supported in Python as well. So how does that work? Well, so you still have the client server concept, and every call and return is turned into most likely TCP/IP type of thing, but with some packaging. So what do you have to do? Well, what you do is what's called a stub function, in the sense that when you make a call, you only make the call on your local machine. But that call is not the real call. It's called a stub call. Why? Because it's only an agent. It takes the parameters you pass to it and then package things up into a message, which then is sent over TCP/IP like you saw earlier, the client server, to the server, and then the server takes apart and then reconstructs the objects, and then maybe it has to take care of the calling convention and then packages them into the convention accepted by the code, such as COBOL, whatever, and then so that the COBOL code can actually run it correctly, puts it in certain format and so forth. So this kind of packaging and unpackaging is called marshalling and demarshalling. Marshalling means packing these parameters into a message, whereas demarshalling takes apart that packet and then turns them back into data objects. And it may have to do type checking as well, and also the different representations. Because when you call from, say, Intel machine to a PowerPC or some other, your integers may be represented in entirely different ways, right? And also there's other encoding, even character encoding could be different. And so those translations have to be done in the process of marshalling and demarshalling, okay? And also return value and so forth. So data representation is an issue, integer, floating point, and also if you ever call a function with pointer, what does pointer mean? I mean, it's an entirely different machine. So to me, I may say, okay, whatever data you have, put it in this pointer address. It's like, what? The remote call can't access your memory because it's over the network. So what do you do with the pointer, right? And also, your connection is not always successful, right? So what happens if you make a call that's not successful? Or maybe, I mean, there's different ways of being successful or not, right? And so do you retry? What do you do, right? So the RPC library will have to take care of that, right? So it presents some reasonable implementation, and then in the worst case, just have to tell the user, sorry, can't do this, right? Okay, so data representation. So nowadays we use ASCII, well, more than ASCII, Unicode. But before Unicode, there's different representations, right? There's all sorts of different languages. And even, I mean, in the US, ASCII wasn't the only standard just for US character set. IBM mainframe actually has its own EBC, DIC character encoding. And so that has to be adjusted because a lot of times you're running legacy code, and that was written in those old standards. Or integers is a big one because Intel machines are what's called little endian. What that means is if you have integers, it could be 32-bit, 64-bit. Do you put the least significant byte first or most significant? So if you put the least significant byte first, then that's called little endian byte order. If you put the most significant, that's big endian byte order, right? You must have seen this in architecture classes. And so that means I can try to pass an integer, but then to you might interpret it the opposite way. So for network purpose, for marshalling, demarshalling, everything nowadays gets converted to big endian convention, and if it's a little endian, it gets converted back. Right, and so that just because there are more companies that do big endian and little endian. Floating point may have different sizes too, right? And so there's these representation you have to convert to and from. And also pointer is only meaningful in the address space. So what can you do? Well, you could either limit the pointer usage, say no, not allowed, or you can limit to certain types, or you could maybe associate certain buffers, but those get a little tricky. So most of the time you just say, no, forget it, don't use pointers. Another is communication issue. So RPC may fail, but what kind of failure? So it could be that when you try to connect, you couldn't connect to it, or maybe connection is successful, but then the reply path is broken, right? So that means you can't just keep retrying. Why? Because if I make a call and it doesn't come back to me, do I really make another call? Well, as far as the server is concerned, there's a difference, right? Because if I make a call and then the result is not returned to me, and I make another call, what could happen? I mean, you know this when you purchase something online, right? Say they tell you, do not hit another submit button, otherwise you buy 2 copies of your whatever item, right? So you could get charged twice, which is probably not what you want, right? So, and then you say, wait, couldn't I just rely on acknowledgement packet coming back? Well, acknowledgement could be the one that gets lost, right? So, so there's different failure modes, and so what do you do? Well, the basic thing would be you need to at least track some kind of timestamp or sequence number so that, and then you also do it in conjunction with acknowledgement so that it's like e-commerce. You don't click another type, or if you click another time, the server is smart enough and says, okay, well, this guy tried to make 2 copies of buy two things, but they probably don't mean to, so they can block it that way, right? So that's a way, same idea with RPC call. Why? Because these RPC calls could have side effects. Oftentimes these are running on, for big banks or financial records. And so if you make 2 calls unintentionally, that's bad because then somebody's bank account gets deducted too much and then the other doesn't get credited, right? So you have inconsistencies, right? So these duplicate calls are a problem. So both sides really have to synchronize, but the more synchronization you do, the more delay you get. So it's always a little tricky here. But anyway, I just wanted to let you know that there is such a concept, and then acknowledgement is important, and how you balance that with the latency, that's a hard problem. Okay, so that's really what I wanted to cover for chapter 3, and now we're gonna go into chapter 4, which is on threads. This may be a slightly shorter chapter, but there's actually a lot to talk about, especially on the implementation side. So we're going to take a little more time to do threads. And strictly speaking, the threads don't have to be part of an OS, but because the concepts are so prevalent and they are important enough that most OSs provide some level of support for threads, that's why it gets included in this course. But you can certainly do threads all without an OS, all without any OS support. We'll talk about this. So this is an introduction to threads, different multi-threading models, and case studies and issues. So now what is a thread? Well, a thread is, it could be 2 things. One is just a concept of a fundamental unit of CPU utilization. What does that mean? think program counter. You know what a program counter is, right? So that's where you are currently executing in the program, right? And so by default, pretty much all languages you deal with, whether it's C, Python, everything, assumes by default a single-threaded execution, right? And of course, you start getting newer languages, Golang, others, may execute multiple threads, but still, everybody starts out, or assuming, unless they specify otherwise, a single program counter, right? Somewhere somebody represents, whether it's a virtual machine keeping track of this, or if it's a CPU native program counter. It's a fundamental unit of CPU utilization. So in fact, you don't have any threads, package support, no library support, it's running single-threaded. That's a concept. And then people are trying to make, okay, now, given this single-threaded execution model, can I magically make multiple program counters that run different parts of the program concurrently? So I have maybe 10 program counters, all associated with the process. So one thread runs the program counter here, another thread runs another part of the program, another thread runs something else. Well, you do need some code to support this, some library support, and that code needs to support the abstraction so that each thread thinks it has the same environment as if it was running single-threaded, right? So that concept of more artificial thread, that's a created concept. That's a software abstraction, right? And so thread does mean these two things, but yeah, you got to know depending on the context. And then we will look at some API examples, and pthread will be revisited several times. Pthread stands for POSIX threads, not Python threads, even though I like Python a lot. It's POSIX. And why? Because it's important enough, it's running on pretty much all OSs. There's implicit threading. Some OSs try to support, because I mean, threads are kind of troublesome to manage, even though, say, in Python, it's actually not too bad. Still, when you write a program, it's kind of a hassle to have to think about multiple threads. So some languages or some runtime systems just say, okay, here, just show what you want done, and then the runtime support will take care of starting threads and destroying them. And then we'll see case studies of different threads libraries. So why would you want multiple threads of execution, say, in the process or on the system? Well, one is it's really to meet the needs of modern applications. Modern applications oftentimes have to deal with multiple aspects. For example, what user interface is one aspect they have to deal with. There's the network side. Maybe there's an I/O side other than network. Maybe they have to run other things. So, for example, a lot of signal processing you may have seen, they do multiple stages of transformation, right? And so, and when you write the code, you just want to think input, output, and you don't want to have to think, okay, well, how do I do this? Because if you do think input, output, and compose them, it's much more modular. And these things all make progress at the same time. And so you say, well, we could do that as processes, right? Yes, you could. But what happens? Processes are too heavyweight, and you saw interprocess communication. Even setting up shared memory is a lot of hassle. I mean, do you even remember what I showed? Even I don't remember the details. I can't even memorize, right? I have to go back to the source code. So it's not something that's so easy to do. And also you get into race conditioning, which we'll see in a few weeks. And so that means just having things run concurrently, that's, tricky, and it's a heavyweight. So to solve the problem, let's solve one problem at a time. So heavyweight, let's try to solve that problem. And because process creation involves what? Well, creating the process, remember, do by fork. Fork duplicates the process, and then if you want to run something else, it wipes out and then reload something, right? And then you set up all these things to cross. But if you're running the same code, that communication is still costly, right? And also context switching, that's much more expensive. So threads are much lighter way solutions to the need to run multiple things concurrently within an application. So the word task is a vague term. Linux uses tasks to refer to both threads and processes. We'll talk about that later. But so threads are a good idea for allowing you to have concurrent things going on inside the same program. They may share data. But conceptually, when you write the code, you don't have to think about, okay, what do I have to? I have to jump here and then jump there, jump there. That makes your code very hard to maintain. Here, it makes your code much more modular. We'll see some examples, okay? And even kernels become more multi-threaded just because of these what you call multi-core architectures. So some people call threads lightweight processes, but the term lightweight process actually has other specific meanings. So I try to avoid lightweight processes, but people use the term informally to mean threads. Okay, so you just have to understand their context. It's a basic unit of CPU utilization. What that means is, right, so if you don't do anything, you have one thread running. No need for any other support. It's just one thread because CPU does have a program counter, and that's assuming just one thread of control. And now if you want to create multiple threads of control so that you can simultaneously be at different parts of the program, that's okay too. This threads library is what allows you to do that. And so that means, well, the threads in a process share code section. What's code section again? It's a program, right? Program binary. Data section, well, your data, right? And then open files, so these would be any resources they requested from the OS. Signals, and I'll talk about signals. Basically, these are the kind of the callback. So you want to be notified of certain OS events. Those are called signals. Okay. So again, those are concepts constructed by the OS. So all of them, all the threads in the process share those resources. They see the same memory, same everything. Although there may be some restrictions. Now each thread has to have its own state, and well, thread ID, strictly speaking, not part of state, it's just identification. But it has to have its own program counter. By that I mean the program counter value. It gets loaded to the actual program counter register, unloaded and saved, right? So, but its own program counter value, its own register set, right? Remember on the 8051 you have R0 through R7, a few other registers. And we'll revisit 8051 soon. It has to have its own stack as well. Okay, so that means, on system startup, you may have one that gets you started, but then for each thread, you have to allocate a chunk of memory, and then when you're running that thread, move that stack pointer to that stack for the thread. Okay, so that when it runs a function call, it can push argument on the stack, return address on that its own stack, and return pop from that stack. And you switch thread, you save that stack pointer into its thread control block. Then load the saved stack pointer for another thread so that you can run. Right? So it's kind of a baby context switch in that sense. But in the same address space. So you can imagine PCB, remember from last week, program control block, it's a record for saving the state for a process. Now you have thread control block, again, this conceptual, that saves the state for a thread. Okay. Now, example applications that use threads, very often web browsers. Right? Because you would have, nowadays you may have multiple windows open, even tabbed windows. And while this one's loading or playing YouTube, you might be loading up another browser window for something else, right? Each one would run its own thread. And maybe one or more would display the content. Another would be loading from the web. Another might be processing or parsing or rendering the HTML or even JavaScript and so forth, right? So it's useful to do these things concurrently. Now, web server is another example that uses the threads often. Why? Because it takes time to load and serve the page. And when you write the program, you want to think, oh, I'm just serving this request. You run it as opposed to, okay, I should respond, read, and then check if another thread needs to make a request. Another thing makes a request, another request comes in, right? Track different states in one single thread program. That's too messy. Much better if you say, okay, let me start a new thread just to dedicate to another request so that it can go through its flow, right? Different stages, and that program is much easier to explain. And besides, these different threads run independently. There's not a lot of dependency needed. And so, yeah, here I want to introduce the term spawn a thread or spawn a process. That's another word for creating and starting and running, right? And so spawn is more of a biological term, like fish spawn little fish. Anyway, so if you do process too heavyweight threads, another advantage is, well, guess what? A lot of these threads are of the same type, right? Could be serving web page. In fact, could be looking at the same web page. If that's the case, great, because you don't have to create a separate process just to reload things into its own address space. It's already in that address space, right? So that way, it's running the same code. You don't even have to duplicate the copy or do the context. It's in the same context. And then you might have some page caching inside your process. So that way, if it's a popular web page, then a different request comes in. Well, guess what? It's already in memory. Serve lowers your latency, and so everybody wins, right? So this has a good, better sharing of code and resources and maybe data. So back to RPC server. That even though the book puts it in the process section, guess what? It's much more appropriate to implement a lot of these RPC in using threads. So different RPC requests come in to the server. The server will just then start a different thread to handle this marshalling, demarshalling. So it has its own stack, its own little memory, but then they share the code. So that's a good thing, right? So multi-threading, responsiveness, as I said, because, well, even if you're not doing a server, still good to have multiple threads in the sense that if you have a thread that's blocking for some reason, could be system call, could be something else, at least there's a possibility of running a different thread so that it can continue making progress while this other call is pending. Resource sharing, you've seen in the case of a server, even browser as well. So that way you can run code in the same address space. You don't need separate copies of the code. In fact, data caching could also be beneficial. Economy in the sense of lighter weight. You don't need to occupy additional memory or additional process control block. You do it all within the process. In fact, there's 30 times performance difference. So process creation on Solaris is 30 times as slow as thread creation. Which one would you rather do, right? So you can have 30 threads for the same cost as running one process. Which one would you rather do, right? Context switching with process also much more expensive, 5 times slower than thread switching. You say, what, really only 5 times? You would imagine probably heavier. Well, okay, it may be, but still, that's I think an optimistic case. In practice, it may be even a greater difference. And now threads with switch register set, but not memory management, because there are a lot of costs you pay in process context switch, as we'll see later, is actually how you manage the virtual memory. And it just becomes heavier weight. Now scalability in the sense that now there's a trend towards multi-core. Most of the laptops you get are at least 2 cores, if not more. And that actually is a good match with threading model. So here's additional comparison. AMD 2.4 gigahertz Opteron, IBM 1.5 gigahertz power 4 architecture, Intel Xeon 2.4 gigahertz, or Itanium 2, right? You can see speed up it varies. Like fork is 17 times to 104 times more. P-thread create is 1.4 to 2. So, it could be 30, 50 times difference. Right? So it's pretty dramatic. And also the communication can be different. Maybe not as much, but still pretty significant. Okay? So good reasons for using threads. Now, threads are not automatically beneficial. If you're not careful, you don't know what you're doing, threads could actually slow you down. So it always comes back to this load balancing or computation partitioning issue. And in fact, I included a few experiments for you to try just so you can see for yourself. By running more threads, you're not necessarily getting more gain. Sometimes it slows you down because it's not for free. And also balancing is an issue, right? Is the workload evenly distributed as much as possible? If not, then you're not getting the potential speed up. Or sometimes it's the data properly partitioned. If not, you're not getting the benefit. A lot of times it comes back to data dependency. How much synchronization do you need? Because every time you synchronize, you're waiting for somebody, right? The faster one waiting for slower one. Also, testing, debugging can be very tricky, although there's been progress in recent years. GDB or a few other debuggers do support or have some concept of threading, but still it's very tricky. Now, so concurrency versus parallelism, you got to know this concept very well. So what's the difference? Concurrency just means you have multiple things, you might call tasks informally, that are active at the same time. Now, just being active doesn't mean it's running, okay? It just means it's somewhere being alive. It's not dead yet, not completed yet. Somewhere, could be running or could be waiting, but it's active. In other words, it has state, that's alive, right? And so you can have concurrency so that, really that's for you to track where multiple things are, right? So that's where you have multiple program counters. That doesn't mean all the program counters are moving at the same time. That's parallelism. So if you have multiple execution units, then yes, they could be making progress at the same time. Then that's parallelism, okay? So parallelism refers to multiple simultaneous progress, right? And so you do need multiple workers. Otherwise, you're just switching between them. That's called concurrency. So before parallelism, you actually have to identify concurrency. So you have to structure your code at least in a concurrent way. So that way, on a processor with multiple execution units, you have the chance of executing them in parallel. Okay, you see the difference now? So parallelism means there's actually simultaneous progress by different execution units, where concurrency does not automatically imply parallelism, but it's a requirement for parallelism. Right? If things are not concurrent, you can run them in parallel, period. Right? So that's kind of a purpose of threads. So you at least structure things concurrently, so you have the chance, it's a bonus, right? If you happen to run on a multi-core architecture, yes, you have a chance. It doesn't automatically say you will automatically get parallelism, but you have the chance of running in parallel and potential speed up. Now, multi-core architectures usually refer to something that shares physical memory, and that represents a good match with threads. In fact, this is what might be called hardware threads. Now, threads started out as a software-only concept for converting a single-threaded program into one that has multiple threads of execution, right? That's a software concept. But now the underlying architecture starts supporting multiple cores, and people are saying, well, let's have them make progress in parallel, right? Not just concurrent, not just switching between them. So multi-core architectures could support simultaneous execution of these threads, even within the process. So you have chance of speeding up. And that's actually a good match with it because they share memory in the first place anyway. And that way it's good for cache behavior because then you share the same code, you're likely to have more cache hits. Now there's different kinds of multiple hardware threads. So there's something you may have heard of or may not, SMT. It stands for simultaneous multi-threading. Now SMT, this is not an architecture class, so I'm not going to tell you too much about it. An example of SMT is Intel hyperthreading. But SMT actually came way before in the older supercomputer like Terra machine you may or may not have heard of. They already had SMT. What does that mean? That means on a heavily pipelined machine, you're going to get pipeline bubbles. And that's when they sneak in the bubble, okay, but sneak in another thread and then fill in that gap. So that way, it's really a way to keep your pipeline heavily utilized as much as possible. But it doesn't necessarily have different cores. It's the same core, but pipelined. And in a sense, yes, it has it's divided up so that different pipeline stages run in parallel, right? So it's kind of a trick to utilize your processor more to fill the pipeline bubble. So it's better than leaving the bubbles. Otherwise, you're not doing much work anyway. And sometimes these bubbles are pretty long, right? What could be an example? Your memory load and store, right? If you do cache, it's a few cycles. If you do main memory, it could be 100 cycles. What do you do with 100 cycles? Well, you fill in another SMT thread. That's a good use. So it's a kind of a good bang for the buck in the sense that by it's just sticking this, utilizing the pipeline bubbles, you actually can sell for more money, right? So it's a good win. And it's not the same as having two cores running simultaneously, but it's actually, no, in fact, SMT can support multiple of these as well. So with a little bit of hardware support, SMT, like Intel hyperthreading, can say, hey, I got 4 hyperthreading cores. You say, wow, great. Well, no, you're not getting multiple cores. You're just getting hardware threads. Does that make sense? Okay, so now, but then, of course, silicon became much cheaper, and then multi-core is less of an issue. So then you have true parallelism. So that's with multi-threading with a multi-core architecture, not just simultaneous multi-threading. So the point here is that SMT is somewhat of an orthogonal concept to multi-core. Each multi-core can be an SMT processor, okay? So that SMT just means you're filling the pipeline bubble with another thread or a few other threads too. But multi-core tends to be making more progress because SMT is really like any leftover wasted when you fill it. So you're not going to get the same kind of speed up as you would with a multi-core, okay? Now, there's different kind of parallelism. Roughly data parallelism on one hand, task parallelism on the other hand. Now, data parallelism means you can partition up your data so that the same task, or more or less same task, can work on different parts of the data independently. What would be an example? So you probably know about matrix multiply, right? And so matrix multiply basically is a bunch of dot products or inner products. You take one row, one column, do a dot product on them. What's a dot product? So the corresponding elements you multiply and then sum their products. That's a dot product. And then you deposit it in the particular target location of the new matrix. And so yeah, there you do have quite a bit of data parallelism, even though a few of them use the same row or same column. Still, you can perform these dot products in parallel. With the little data duplication, perform them simultaneously. And when you write to them, you're writing to distinct locations. So there's not a conflict right there. So even though you can spend time serially to do this, you can parallelize this. Okay, so that's an example of having data parallelism. And it's the same code, essentially, right? Just doing dot product. Now, task parallelism, on the other hand, means you take a problem and then decompose them into distinct tasks that they should be running independently most of the time. Once upon a time, they exchange data, but with enough buffering, you probably don't even have to wait for each other. And so one example, like we mentioned earlier, you have these servers, right? So HTTP, FTP, or cloud drive streaming and all that, right? There's different stages. Some working on networking, some doing the parsing, some and then fetching. Right? These are more or less distinct tasks. Yes, they're just flow between them, but still, and multimedia is another one, or gaming, right? Because why you may need some thread to do audio processing, right? And MPEG, MP3, or whichever, and video is done. Graphics is very different, right? And also, you're doing rendering or doing the video decoding, texture mapping. These, a lot of these are distinct. You can process them independent of your audio stream, right? And then gaming, the game rules would be something distinct, although the game rule ultimately determines what you need to do in the rendering, the audio, and other things, right? Now up to a limit, because these can't just run on their own. They have to synchronize once upon a time, right? So every frame, every couple of frames, they have to synchronize. Otherwise, you can have the audio keep playing, and then it's a few seconds out of sync with your image or rule. You hit a button, it doesn't respond until 5 seconds later. That's not acceptable. So they have to be synced up. And so, strictly speaking, this is not a strict task parallelism or gaming or multimedia. You have task parallelism up to a certain extent, but they have to sync up. You can pipeline these so that they don't have to sync up so often. You can be a few frames ahead. But every time you sync back up and then you restart in parallel, that's called fork join parallelism. Now, don't let the word fork confuse you. This is really describing the pattern of taking one and splitting into multiple threads. It has nothing to do with the Unix fork. Okay, the term exists way before Unix fork was invented, but sometimes they're called series parallel type of parallelism. Okay, but fork join is probably a common term, and it's not necessarily an OS or threading concept. It's in other languages. There's a language called Occam and a few others that do support fork join parallelism. Now, there's also pipeline parallelism. The book doesn't really say this, but this is really somewhere in between task and data, in the sense that you divide a task into stages, and you know this from your architecture class, supposedly, or assembly line, so that you take a stream of things coming in, divide into these stages. Each stage does its part, sends to the next stage, and then the next stage, so that all the different stages can carry on in the steady state. Initially, you do need the startup cost, because the earlier stage, if they don't have anything, the later stage has nothing to do, right? So you do have the startup cost, but usually that's easily amortized over your steady state. And assuming you have a steady stream of things coming in, and 3D graphics pipeline for gaming fits this pipeline parallelism, because you can do application, geometry, rasterization, all these. So in graphics class, you'll learn about these graphics pipelines. Now, series parallel or fork join parallelism, I talked about it. So basically, you run serially for a while, you fork threads, informally use the term fork, or you spawn threads. So you can run things concurrently, hopefully in parallel, if you have the right execution structure, then join them, and they come back to serial, and then you can keep going for a while. And this can be done recursively as well. And so this is common for divide and conquer type of problem. You should have seen this in your algorithms class, like your merge sort is a typical divide and conquer problem. Quick sort is another one, but difference is it's only divide. Conquering part, you don't need a merge. Once you do the pivot partitioning, the rest can go on independently. There's no join, it's just fork, okay? Merge sort does need the merge part, which is the conquering part. So yes, you can divide and then have them do this in parallel, but then you have to do the merge sideways. So that's a bottleneck. So quick sort, one reason quick sort is quick, it really is that once you do partitioning, the other sides can run on their own. No need to join. I mean, eventually you need to know what's done, but there's no additional dependency. And you get to have a little fun this week with quicksort. I give you the source code, you can try it. And support as fork join construct in some language or threads package. Okay, merge sort, you divide 8 into 2 halves, left and right, and then recursively call on these. And so left and right can run in parallel, but they have to synchronize before you can do the merge. Okay? And so that synchronization is what's somewhat costly. Okay, now there's concept of user threads versus kernel threads. Initially, there's only user threads. Why? Because people don't want to pay the cost of going to kernel. They don't want to pay system call cost. You remember, system call requires switching to kernel mode, right? Saving state. It's like an interrupt, not cheap. And then coming back, another restore state, right? So they initially motivation was just so that you can have multiple threads of execution within an otherwise serial process. So it was all user threads. And so the OS actually doesn't see threads, just sees a chunk of memory. And it saves whichever PC value is whichever thread that's currently active. How you use other memories, none of the OS's business. Okay? And so that was the case with a lot of these other threads. Now, kernel threads, on the other hand, is a slightly newer invention. Now, this was actually independent of whether you were running on multi-core or you have any hardware threads. No, it's just taking the concept of threads, but then implement it in the OS. Okay? Why? Because OS actually has concurrent activities as well. If it benefits the user level, benefits the kernel as well. Makes the code easier to explain or easy to reason with. So I'm doing this network activity, put a thread on it. I'm doing file, put a thread on it. So kernel can benefit from multi-threading as well. And so it's not necessarily that you want to run on a multi-threaded hardware architecture. Okay, this was not necessarily done for speeding up purpose. Okay, it's really just so that since it benefits user, benefits kernel, do it in kernel. But doing it in kernel, it actually the next step is they say, well, we could actually share some of the thread of control with user level, right? What would be an example? So user makes a call, blocking call into the system. What does that mean? Even though the user process is multi-threaded, guess what? That whichever active thread going into the system call gets blocked. So the entire process blocks, right? And so what happens? Well, the kernel actually has the option of saying, oh, okay, I know this thread is blocked, but I'm going to be nice. Let me assign another thread so your other process, the user level, can make progress. You don't have to get stuck just because initially I only gave you one thread. So there could be mapping between kernel threads and user threads so that even on a single core processor, it allows the user process to continue making progress with other threads that are not supposed to be blocked. Okay, so that's called scheduler activation. We'll talk about that later, and the book has a description on this as well. But of course, multi-core and SMT architecture come along, and guess what? Well, you can map the kernel threads onto these cores, additional benefits, right? So that's why OSs get involved in this, because it's not just a user level concept that can benefit from this. Kernel benefits from this as well. It can do things not just concurrently, but in parallel. So kernels do this. And then they can share these benefits with the user process, with the proper communication. Okay? So pretty much all modern OSs support kernel threads. Whether or not they share their kernel threads with user threads, that's a different issue. Linux doesn't do that, but a lot of other OSs do. Right? So user threads implemented with the user thread library. The kernel doesn't have to know anything about it, but it could, and that's with scheduler activation. So if the kernel doesn't know anything about it, the user process is assumed to run single-threaded, so that when a user thread blocks, what does that mean? That means the entire process blocks, right? So simple as that. Even if there are other threads ready to run. Kernel threads, on the other hand, managed by the kernel, and so the kernel threads library can actually decide how to manage them, and then when threads block, kernel actually can schedule other threads to run, including allowing the user threads library to run. But there has to be that interface. Okay, but kernel threads, if you have to switch to kernel to get the thread benefit, you pay a price for it. So whether or not it's worth it depends on the implementation. Okay, let's take a break here. We'll come back in a few minutes.